net stabilizing moment, which is obtained by taking resistance moment minus overturning moment. Now, moment due to resultant force is obtained by taking this resultant force times perpendicular distance. Now it will be equal net force times perpendicular distance. It will be equal to net stabilizing moment, which resistance moment minus overturning moment. But this resultant force, it will be equal to total weight which acting at is retaining more. This resultant force times, it will be equal to net total weight. Net for resultant force will be equal to total weight of the total weight which acting at is retaining, which is 61.9. Now it will be equal to total weight times location of the resultant force, resistance moment of overturning moment. So to obtain this one, it will be equal to resistance moment minus overturning moment over total weight. Now, resistance moment is 822.5 minus 166.2 times over total weight, which is 61.9. Now, the allocation of the resultant force, it will be equal to, now let's compute 822.5 minus 166.2 divided by 61.9. It will be equal to 1.813 meter. Now, the next determines the eccentricity. This is eccentricity. Now, this is eccentricity. Eccentricity is obtained by taking the distance from this point up to this point is a half of the width of the base minus the location of resultant force, so as to obtain the value of eccentricity. So eccentricity is obtained by taking a half of the width of the base minus location of the resultant force. So eccentricity will be equal to a half width of the base is 4 divided by 2 divided by 1.813. It will be equal to 2 divided by answer. It will be equal to 0.187 meter. This is eccentricity, 0.187 meter. Now, before applying, because as I said before, this formula is applicable if this resultant force lies within the middle set. How can we know that this resultant force lies within the middle set? By using this concept for the middle set. Eccentricity should be less than or equal to base divided by 6. By using, if eccentricity is less than this one, it confirms that then the resultant force lies within the middle set. Now, base over 6, base is 4 divided by 6, it will be equal to 4 divided by 6, it will be equal to 0.667 meter. And eccentricity we have obtained, which is equal to 0.1787. This is less than 0.66. Hence, the resultant force lies within the middle set. Within the middle set. Since the resultant force lies within the middle set, the next determines the maximum pressure and the minimum pressure from this formula. Net resultant force over base 1 plus or minus 6 times the eccentricity over base. Now, how to determine? We use for maximum if we take for plus, and the minimum pressure is obtained by taking negative value. So maximum pressure, it is equal to, this resultant force is equal to the total weight, which is equal to 61.9 kilonewton per meter. Now, maximum pressure it will be equal to total weight over base 1 plus 6 times eccentricity divided by base. Now it will be equal to 361.9 over 4, 1 plus 6 times eccentricity, which is equal to 0.878, here there is 1 over 4. It will be equal to maximum pressure, it will be equal to 116 kilonewton per meter square. Now, for minimum pressure is it will be equal to total weight of base 1 minus 6 times eccentricity divided by 2. It will be equal to 361.9 over 4. 1 minus 6 times 0.187 divided by 4. The minimum pressure, it will be equal to 65 kilonewton per meter square. No, let's check for the bearing capacity if maximum pressure is less than allowable bearing pressure. So maximum pressure we have obtained, which is equal to 116. This is kilonewton per meter square. This is less than allowable bearing pressure. Allowable bearing pressure, which was 120 kilonewton per meter square. Hence, this retaining of ferro mold, it is okay. The bearing capacity for this retaining mold is okay. After determining this, after checking for the stability, the next step is designing of reinforcement. Step number 3, design of reinforcement. Design of reinforcement. Design of reinforcement. Design of reinforcement. This design of reinforcement will be in the design of reinforcement will be required to reinforcements for steam wall and reinforcement for the base. Now let's start with steam wall. Reinforcement for the steam wall. Reinforcement for the steam wall. Our retaining wall was in this way. And this is a steam wall. That's which is going to determine its reinforcement, which will have a height of 5 meters. 5 meters. So its pressure diagram will be in this way. This is pressure diagram of this. Because the steam wall, its height is here from the ground level up to the height of 5 meters. This is the height of steam wall. Now this is active pressure which acting, and this is a horizontal force due to the soil pressure. And this is H over 3. Now let's determine the first step. During the design of reinforcement of steam wall, the first step, let's determine the soil pressure as active pressure. Active pressure is obtained by taking unit weight times coefficient of active pressure times height of steam. This which are 5 meters. Now active pressure will be equal to unit weight of soil times coefficient of active pressure, which is 3 times H of steam, which is 5. It will be equal to 19 times 1 over 3 times 5. It will be equal to 31.67. This is kilonewton per meter square. The next determines the horizontal force due to the S pressure. The horizontal force is obtained by taking the edge of this pressure diagram. Because it is triangular, so it will be equal to a half times base, which is active pressure times H. So it will be equal to a half times 31.67 times H, which is 5, times 0.5 times 5. It will be equal to 79.17. This is horizontal force, 79.17. This is kilonewton per meter. Now let's determine the maximum pressure. The maximum pressure for this system, the maximum pressure, no, the maximum moment. Maximum moment is obtained by taking this horizontal force times perpendicular distance. Horizontal force, which is Fa times perpendicular distance h divided by 3. So it will be equal to 79.17 times h, which is 5 divided by 3, times 79.17 times 5 divided by 3. It will be equal to 131.95. This is kilonewton meter per meter. So to obtain, because we are going to design for the reinforcement, and this retaining wall is subjected to unit weight of this structure. So we multiply by the factor of safety for the dead load. So the design moment will be equal to factor of safety, which due to the self weight, which is for dead load, times this maximum moment, which is 131.95 times 1.4. It will be equal to design moment. It will be equal to 184.7. This is kilonewton meter per meter. This is design moment. Now, after obtaining the design moment, the next step will determine the area of reinforcement. Area of reinforcement is obtained by taking maximum design moment over 0.87 FYZ now, but effective depth is obtained by taking the thickness the thickness of this system, which was 500, minus concrete curve of the steam, minus 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 diameter main reinforcement divided by 2. So it will be equal to 400 minus cover. The curve of this steam was 35. This one was 35. So we minus by 35 minus 20 divided by 2. The diameter of main bars was 20. So it will be equal to 500 minus 35 minus 10. It will be equal to 355. This is millimeters. This is effective depth. Now let's determine the value of Z. The value of Z is obtained by taking effective depth times 0.5 plus 0.25 minus K over 0.9. K is obtained by taking maximum design moment over SU BD square, which is 184.7 exponent 6. So as to make it in Newton per millimeter over FCU is 35 times times this width, because this retaining wall we are designing as for slab. This space which is taken by is 1 meter, which is equal to 1,000 times 1,000 times effective depth, which is 55 square. Now the value of K will be equal to 184.7 x 0.6 divided by 35 times 5,000 times 355 square. It will be equal to 0.048. Now, if you substitute this value into this formula, the value of that will be equal to 0.95 times effective depth. This should be less than 0.95 times effective depth. So the value of that will be equal to 0.95 times effective depth, which is 355. It will be equal to 0.95 times 355. It will be equal to 337 millimeters. This is the value of Z. 337 millimeters. Now, let's substitute into this formula so as to obtain the area of reinforcement for steam. So it will be equal to maximum design moment, which is 184.7 exponent 6 over 0.87 times Fy, which is 500 times the value of Z, which is 7. It will be equal to 184.7 x 0.6 divided by 0.87 times 500 times 7. It will be equal to 1260 millimeter square per meter per meter. Now, this is area provided for the stream, which is 1260 millimeter square per meter. Now, let's determine the area required for this steam wall with and its spacing. Now, because we have obtained this value, so let's determine from this table the area required, because our area is per meter and this for bed. So our area is 160, which have with a diameter of 20. So the area from this is diameter of 20. This is diameter of 20, and this is a cross-section area, and this is the spacing required for that area. So this is diameter of 20. Let's determine our area was this one. So for the design area should be greater than or greater than closer to the area which was provided. So it will be this one with a spacing of 200 millimeter. So it is the area provided. Therefore, we say that provides H with a diameter of 20 at a spacing of 200 millimeter center to center, which gives the area of this one. This is greater than this one, so it will be equal to 157. This is millimeter square per meter. This is the area required for the steam wall. The next step is to determine the area. Determine the reinforcement for base. Reinforcement for base. Base reinforcement. Base reinforcement. Base reinforcement. This base made up. This is a base. Base is made up of heel slab and toe slab. Now let's start with heel slab. hill slab. This hill slab, this hill slab. Hill slab is hill slab. Now let's consider the base. Is a base because we are dealing with the design of base, so we consider the base only. This is a base, and this hill slab is act as cantilever, which is fixed at stem wall. Now let's say this point A, point B, point C, point D, and this is what? This is toy, and this is heel. This is heel. Now in your case, we are going to design for the heel slab. After that, we design for the toy slab. This toy slab, heel slab. Now our target is to determine the reinforcement for this heel slab, which have its width on this way is up to this or 0.4, 0.7, 0.4, 2.9, 2.9 or this way. So its pressure diagram is pressure. The pressure beneath the base usually varies linearly. Varies linear. This is the pressure. So its pressure diagram, because varies linear, it will have maximum pressure and minimum pressure. Maximum pressure and minimum pressure. So the soil pressure beneath the base varies linearly. So this is minimum pressure. Minimum pressure, which was 35 kilonewton per meter square, and this is maximum pressure, which acts at toy. Maximum pressure, which is 116 kilonewton per meter square. So the pressure increases from the heel up to the toy. So because we are going to design for the heel strap, and we are going to design for the heel strap, and this heel strap is act as cantilever, which is fixed at stem. So its maximum moment it should be at point C, at a point where is fixed at stem. So maximum moment will be at this point. So we are supposed to determine, we design the heel strap at point C. Let's say this will be determined the pressure at point C. Let's say pressure 1 here at toy, pressure 2 at heel, and pressure 3, design pressure at point C. So how can we determine the design pressure? The design pressure at toy, pressure 1, is obtained by taking this pressure times times factor of safety for the dead load due to the self weight. So 1.4 times 116, it will be equal to design pressure for the toy. So 1.4 times 116, it will be equal to 162.4. This is kilonewton per meter square. Now the minimum pressure at high is obtained by taking factor of safety times 65. It will be equal to 91 kilonewton per meter square. Now let's determine the pressure at maximum or at fixed point at the point where the heel slab is fixed at stem. So which is pressure 3 is obtained because the soil pressure increases from the minimum pressure up to the maximum pressure. So to obtain the pressure at this point, it will be equal to minimum pressure, which is pressure 2, plus change in pressure 1 minus pressure 2, times the weight of heel slab, which is 2.9 over total width of the base. So pressure 3, it will be equal to pressure 2, which is 91 pressure plus 162.4 minus times 2.9 divided by 4. Okay, 162.4 minus 91 times 2.9 divided by 4 plus times 91, it will be equal to 142.6.76.8. This is zero point 0.8 kilonewton per meter square. And the pressure at point C, which is pressure 3, is 142.8 kilonewton per meter square. After that, because we are our aim is to determine the reinforcement for hail slab, and the maximum moment is obtained at the point where this hail slab is fixed at steam ore, which produces maximum moment. So design moment at point C. Design moments will be able to determine the design moment at point C. At point C, let's say this moment at C. This design moment at point C is obtained by taking here the laws, the width, the soil, the width of base, and here there was the weight of soil, which was acting weight of soil due to the hill slab. The weight of soil was 275.5 this kilonewton per meter, and the weight of base was 38.4 kilonewton per meter. Now let's determine the moment at point C. The moment at point C. So is obtained by taking the moment is obtained because all of these loads which acting at the hill slab will rotate about point C. So there is moment. Let's start with moment due to the soil pressure. Moment due to the soil pressure. Due to the soil pressure at hill. Let's say this is moment 1. Moment 1 is obtained by taking the weight of soil times perpendicular distance up to this point. Perpendicular distance, because it acts at the center of the width of the hill, so it will be equal to weight times perpendicular distance, which is 2.9 divided by 2. So to obtain the design moment, we multiply by the factor of safety. So it will be factor of safety times weight of soil, which is 275.5 times perpendicular distance, which is 2.9 divided by 2. It will be equal to 275.5 times 2.9 divided by 2 times factor of safety, which is 1.4. It will be equal to 559.27. This is kilonewton meter per meter. The next moment is the moment of base at hill slab. There is moment of base at hill slab and moment of base at let's because it's here for hill slab with design moment for base at hill slab. Let's say this is moment 2. This moment 2 is obtained by taking because this hill slab is act as the cantilever, which is fixed at steam with uniform distributed load. So its maximum moment will be equal to the weight of base, this one, the weight of base, which was this one, times perpendicular distance, times the unit weight, times the factor of safety. So it will sum to obtain the design moment. So it will be equal to 1.4 factor of safety times the weight of base, which is 38.4 times because this is kilonewton per meter because this is uniform distributed load, so we multiply by 2.9 times 2.9 so as to be kilonewton meter divided by 2. This is perpendicular distance. We multiply this one so as to obtain in kilonewton. But by multiplying by 2, we multiply by perpendicular distance, which is 2.9 divided by 2 up because it rotates up at this point. perpendicular distance from this point to this point is 2.9. Because for base, so we over 4 out of 4 because the total width of the base is 4 and our aim is to design it for the hills. That's why we take this divided by total width of the base, which is equal to 4. So it's to be in kilonewton per meter. Okay, 1.4 times 38.4 times 2.9 square divided by 2 divided by 4. It will be equal to 46.52 kilonewton